Okay, so now let's start moving. We have positive div, and you can see it, right? You can see that the vectors on the right side of this circle are longer than the ones on the left. So there might be an equal number of vectors going in and an equal number of vectors coming out, but it's the length of the vectors. The green is overpowering the red here. And so we're getting a positive, let's bring in a bunch of vectors there. You can really see the green overpower the red there, right? Let's move it up.
Sound like a nature documentary.
What?
You can really see the green.
All right. Look, when I was in Cal 3, I never got to see what div was. So I'm always excited to show what div is. Because the visualization of div, without this, like how do I explain this, right? Okay. All right, so do you see here? Man, we got some really cool stuff happening right in here. Look at this. It's like here comes the red is coming to overtake the green. You got more going in. They're about to balance each other out. There we go. We've got 0 div, and then the red took over, right? So what does this mean, though? I mean, like what? Who cares, right? Okay, so let me back this out. Let's go to 3-dimensional space. So in 3D, now you have a point and you have this epsilon ball around it. And you're taking all the vectors along this ball and trying to figure out how many are going in and how many are going out. So let me do that for you. Right now, we have, now this vector field I think is the vector field from earlier. Look at our div. What is it? 6. We're going to have lots of green when I show you this. So here it comes. Bam. We've got lots of green vectors coming out of this thing. Right? And let's add more just for fun. You can really see the green. I'm going to pull the ball out a little bit so it's not so overwhelming. And you ready to move it around? Let's see if we can get some different div here. Green's starting to fade here. And now we've got the red, right? And now green takes back over. So depending on where you are, right, you've got more going in or coming out. That's div. Seems like the formula for it is so simple, right? Like del dot f somehow gives you that measurement. That's crazy that it's that simple of a computation to figure that out, but that's what it is. Okay. All right, now let's try and understand what the div actually is. So imagine again you're a molecule, right? And you're moving through 3-dimensional space. You've got, first of all, you've got the direction that you want to go, right? Which is the vector field is making you want to go in a direction. You've got the curl that's somehow wanting you to like twist, right? As you go in that direction, it's turning you. And then these molecules to the side of you, look at those as like that little ball where it's either more green going out or red going in, right? So let's say the molecule next to you has a huge negative div, right? Then what do you think your tendency is going to want to be? If the molecule next to you has a huge negative div, what do you think? You're going to be wanting to actually go that way. Like it's almost like gravity. You can almost look at it like gravitation, I guess. It's actually wanting to pull you in there because if it has negative div, that means everything around it wants to go into it, right? Wants to go into that ball. So that means you're going to want to go into that ball because you're right next to it. Now, if that molecule next to you has a huge, like a positive div, then things around that are wanting to go away from it, so you're going to want to move away from that point. Understand? So that's why we call these points either sources or sinks. A source point, okay, so if you're given a point in 3-dimensional space, you calculate the div and it's positive, then the region around the point is called a source. The region around it would be a source, positive. It's like glowing. It's like things want to come off of it, right? It's a source, like heat coming off of it. Otherwise, if the div is negative, things want to go into it. It's like a sink. It's like a black hole, like wanting to pull you into it. Understand? Now, if the div is 0, then the region around the point is called incompressible. Does that make sense? If the molecule next to you doesn't want anyone to leave, and doesn't want anyone in, then it's like almost like stuck, static, fixed, incompressible. Doesn't want to compress, doesn't want to come out, it's just stuck. Kind of cool. We're almost done with this. Awesome. We need to do an example. The div computation is so simple that I think we can be done with this in 2 minutes. All right, let's do the divergence of this vector field. So that's del.f, which is the partial with respect to x, partial with respect to y, partial with respect to z, dotted with x squared yz, xy squared z, xyz squared. And that's equal to, what's the partial of this with respect to x? Just 2xyz. Then plus, now I'm going to do the partial with respect to y of this, 2xyz. Hey, they're all 2xyz, aren't they? 2xyz. So we can add those up because they're like terms. So 6xyz. There it is. So think about this. If you're in the first octant, what's your div? Positive, because your x, y, and z coordinates are all positive, right? So if any point in the first octant for this vector field, you're going to have positive div. And then you can move to like second octant and think about, okay, second octant, x is positive, y is negative, z is positive, so you're going to have negative div. And you could just, if you're just thinking about it that way. All right. All right, we have another version of Green's theorem. Now, Green's theorem, in case you've already forgotten, which I know you haven't because you enjoyed it so much, Green's theorem says that this is equal to line integral over c of p dx plus q dy plus r dz. So that's the vector form of the line integral over the vector field. That's it written in its scalar form. So this is when we just broke up the vector field into its components. So these two were equivalent, but this is saying that that's equal to this. This was double integral over d partial q with respect to x minus partial p with respect to y dA. You know what? I need to scrap the r. Hold on. Scrap this. Green's theorem, we're two-dimensional still. I'm already thinking of the three-dimensional version of Green's theorem. Sorry. This is what we got last class. Last class was that this is equal to this, but that's equal to this. That look familiar, this part? Okay, now this is another way of writing that. This right here is another way of writing that. So if this and this are the same, then doesn't that mean that this is equal to that? Yeah? Okay, do you remember what the curl of f was? It was that big ugly thing, that big ugly formula, right? Had three components to it. If I dot that with k, what's the k? What's the k vector? 0, 0, 1. Then if I dot that big ugly curl thing with this, the only thing left is the third component, which was this. So this is just another way of writing Green's theorem in what we call the vector version, which means everything in here is a vector, as opposed to this, where these are scalar functions, right? Q and P are your scalar functions. But it's the same formula. And then there's another formula that I'm not going to talk about yet. So just keep this on the back burner. It is another version of vectors of Green's theorem, okay? But this time we're using this instead of the notation f dot dr. We're using this f dot normal vector ds, which we will talk more about later. Just for now, though, just keep in mind we will use that later, and I'll show you where it comes from. So we have two new versions, vector versions of Green's theorem. Okay, there's identities. So there, you know, like in pre-cal, you know how we had trig identities? Like sine of this, this, this equals that, and then you had to show it, right? You had to like start with the left side, turn it into the right side. We have lots of identities when it comes to curl and div. Like for example, the div of the cross product of two vector fields is equal to the first g dot curl of f minus f dot curl of g. Like what? Okay, sure. Is it? Yeah, they're saying it's true. Show it. So you start with this div and then you work through the whole thing, and you can at the end conclude, you can get your last statement is actually g dot curl f minus f dot curl g. So I'm not going to test you on this. I might offer this as a bonus question. In fact, there's two problems from the homework that are like this, but they're both odd problems, so I can't offer them. Well, I guess I could offer them for bonus. I'll offer that as bonus. To be turned in at the final exam, only one can be turned in, either 21 or 23. It's a small bonus, but it's optional material, all right? You don't have to do it.
Double the bonus for 22? No?
I haven't looked at 22, so I don't know what it is. But just don't go out there and look up the solution online, because if I look at the solution, you know, and yours is exactly just copied, like I can understand that you're not using your own mind, you're just using that. Because you should actually have to like struggle through this a little bit. And your notation is going to be different than that notation, for sure. All right, that's the homework for that section though. 1 through 7, then 11 through 15, odds. And then those last two are optional. Do one of them for bonus if you'd like. And we are ready. We've got about 30 minutes. I'm not going to be able to do that second part because we need to start this 13.6. 13.6 is going to take us 2 days, at least 2 days.
The stuff like this, what was it developed for a need for science, or was it
For what?
All these calculations? Was it the math first or the science?
And I don't know. It works both ways, yeah. I mean, there's a lot of times the science needs something to help model the situation, but other ways, yeah. I mean, it's two-way highway here. You know, it goes both ways. The thing is, mathematicians like to generalize. So like right now, we're talking about vector fields, 2 and 3 dimensional. Mathematicians want to talk about vector fields in n dimensions and talk about the properties of that. And then when the physicist or whoever comes to them, engineer, and they have this problem, then they just have to say, okay, we've got this structure already, and the question is happening with n equals 3. Like the space is now 3. And so like what do those formulas look like there? And so, you know, I guess it's one hand shakes the other, you know. They both shake each other? Whatever, however that saying goes. How does that saying go? Well, how's it go? You know what I'm saying? You've never heard that saying? You shake hands? Oh, okay, never mind. Okay, I'm going to look it up because parametric surfaces and their areas. Okay, I need you to think back to 10.7. That was, you know, what, last week? 10.7. 10.7, we introduced the idea of vector functions, and we talked about space curves, meaning that you could draw a curve in 2 or 3 dimensional space with a vector function. And we usually use the notation r of t equals the vector f of t, g of t. So you put 2 functions of t in here and you draw something. So can someone give me an example of a vector curve that in 2-dimensional space that we've used a lot? cosine t sine t, right? And that drew a circle, right? Okay. Now, we could do three-dimensional space. We could do f of t, g of t, h of t, and that would still draw a curve in three-dimensional space. So like a line, a curve, right? As t takes on different values of the function generates vectors in the space. The graph of all these vectors is a curve, not a surface. What we are trying to do now are draw surfaces, which we've done before. But we've never been able to draw a curve with a vector function. We've only been able to draw curves with equations. An example of an equation that draws a surface. X squared plus y squared plus z squared equals 9. Draws a sphere, the surface of a sphere of radius 3, right? So that's a surface, but it required an equation in x, y, and z. Another example of a surface, f of xy equals, I don't know, something like 2x minus 3y. And that would also draw a surface. You'd have some surface above the xy plane. So we've done surfaces, but never with the vector function. So how do we do it? Oh, that was just a reminder. Hey, remember when we drew vector curves? And we could do it in three-dimensional space? Okay, those were taken straight from the notes from 10.7. All right, this new concept. What if we change it so that the r, the vector function, we're allowed to plug in two things instead of one? So you know how it's always been r of t? What if instead I allow you to plug in two parameters, u and v? And we just use u and v because that's the standard notation that we use. So we've taken t out and we've said u and v. So we have a vector function that takes in two inputs. It spits out a three-dimensional vector. The first component, the x component, is a function of two variables. The second component is a function of two variables, and the third component is a function of two variables. If you do that, and you let u and v take on different values, you will generate a surface in three-dimensional space. All right? This is how we do it. These functions, these component functions right here, are called the parametric equations of the surface. Yeah, and that is where I'm going to give you, we are going to pause because the book at this point expects that you can draw parametric surfaces, like you're completely comfortable with them at this point, after I give you the definition. And then I'll give you any practice actually taking a surface and trying to come up with its parametric function. So I have a handout now that we are going to go through. Take one, pass it along. Pass one along. Just pass those back. We have plenty to go around here. Now, with what I've passed out, I need to add some labeling to this because the way it appears to you is not enough information for you to do. So let's start with this first one. All right, in these pictures that I have, these match what you have. The red axis is the x-axis, the green axis is the y-axis, and the blue axis is the z-axis. You can't tell from yours, right? The way you can remember that, RGB, red, green, blue. RGB, they use that for coloring, right? Computers. Okay, RGB, red, green, blue. Red, green, blue. Red, green, curl, right-hand rule. Red, green, blue. All right? That's how this picture is going to be. So I want us to draw this surface. It is a solid disk, isn't it? How can we do this using a vector function? So in other words, how do we do this where we have R of u, v, and it's 3 components, and each of the components are functions of u and v. I mean, they could have u in them. Each of these could have a u in it, a v in it, or no u's or no v's. It's really up to us. But they can have, at the most, u's and v's mixed together. So what is the radius of this disk? Can you tell? It looks like 2, right? So this is a disk with radius 2. Is there anything you could tell me just right off the bat about any of these? The y component must be 0 because you are on the xy plane, right? This is flat on the xy plane. That means there is not a z part. I mean, there's a z part, but it's always 0, right? If you're anywhere on this disk, you're y is 0. Yes? Okay. We are 1/3 of the way there. We need the other 2 components. Do you all understand that and agree with that? Yeah. Anyone have a question? What are you comfortable drawing with vector curves? What's the thing that you are very comfortable with? Circles, right? You can draw circles. So could you draw me this circle that would give me the outer part of this disk? That would be the circle with radius what? 2. So don't write this down, but could I put 2 cosine? I can use u or v here, it doesn't matter. U? Okay, 2 cosine u, and then 2 sine u, and let u go between 0 and 2 pi. And wouldn't that draw me just the outer edge of the disk? That's not good enough though, right? I need that and everything inside. Pardon? Oh, I thought you said something else. I thought you said equals. Okay. We need to be able to adjust this, right? We need to be able to draw the circle with radius 2, the circle with radius 1, and the circle with radius everything between what? 0. All of these circles, right, need to be drawn. So we actually want that radius to be variable. So why don't we use that variable that we still have, v, that we haven't used, and take this 2 out and control that number with v. v times v times. Understand? And then what will I let v vary between? 0 to 2. See how that works? So here's the way you can think about it. Let's start out, let's take some examples. Let's say v is 0, right? If v is 0, what's this? What's this? We get 0, 0, 0. Wouldn't that give us the origin? Right? Now let's say that v is 1. If v is 1, then that's just cosine u sine u, right? And now let u go between 0 and 2 pi, and you draw that circle, right? But you have to do that for all v's between 0 and 2, so you're going to draw the whole disk. Y'all like this? Okay. That's it. We're done. This is the vector function. These are its constraints on its variables. And for every one of these, we're going to have the vector function and its constraints. So let's look at the next example. That's about as clean and easy as it gets right there. It's not like they get crazy hard, but you have to understand this. I should state this. You have to be able to draw surfaces with vector curves, or at this point, you're dead in the water. You can't do the next 2 or 3 sections unless you can draw surfaces. All right. All right, in this one, we have 3 vertices of a tetrahedron given, right? Make sure I'm looking at the same thing you are. So this is the point 0, 4, 0. This one is 0, 0, 2. And this one is 3, 0, 0. And then, of course, the origin, 0, 0, 0. So this one is saying, find the vector functions, plural, which yield the four face surfaces of the tetrahedron with these vertices. There are four surfaces for this tetrahedron. We need to come up with a way to draw each of those four, which means we need four different vector functions. We're going to have four different answers. It is not possible for us to draw all of them together at one time with one function. We can only do one at a time. All right, so let's start off with, maybe we can start off with labeling these. Why don't we label the bottom of this one A? Let's label this side, the back side here B. This back side over here C. And then how about the actual face of this thing, D, like the tilted part of the tetrahedron? Let's start with A, because I think A is probably the most comfortable one for us. The surface A lies in the xy plane, doesn't it? So if I draw just that surface in the xy plane, where does it hit? Like, where does this surface hit? I'm going to be at 1, 2, 3, at 3, 0, right there. And at 0, 4, 1, 2, 3, 4. And then I have a line connecting these two. And do you actually know the equation of that line? Y is equal to -4/3 x plus 4. So it's the slope of the line, right? Negative slope, and then the y-intercept is 4. So that's actually what that surface looks like, right? We're trying to find a way of drawing this surface using a vector function. So r of uv equals, and now I need to come up with my three components. All right, which of these components is easy? Z, right? Z is 0. Because it's laying on the ground, so Z is always 0. So think about the x direction here. This is almost like a type 1 region, isn't it? It's almost like a type 1 region. Your x's are bounded between what? 0 and 3, and then your y's are between this and that function, right? Yes? So why don't we just let the x component be u and vary u between what? 0 to 3. Okay. Here's the trickiest part. Okay? This is the part that most students get hung up on right here. What next? The y right here?
Yeah, that thing would be the function, and then we plug in u for x, and then b would be varying. It'd be like from 0 to that function.
You're on the right track. I'm going to do I'm not saying this is what you were saying. I'm going to show you what is incorrect. I hate showing what's wrong, but I need to explain why it's wrong. Here's what students will do that is incorrect. They will put -4/3 x plus 4. And the idea being that, okay, this is very much like a type 1 region. U is going to go between 0 and 3, and then your y is just this curve, right? So it gives you, you're going to stop at these points. That's what a lot of students will do. It's incorrect. And the reason why is this. If I fix right now u to be 0, you get what point? 0, 4, 0, right? Which would give you that point right there, right? Then if I let u be, let's say u is 1. What would happen if I let u be 1? I'd be at 1, so 1, and then you take -4/3 plus 4, so you're subtracting 4/3 from 4, which means you're going to be like 2. Yeah, so you got some, it's up, right? But it's right there. It's on that line, isn't it? Yes? So all you're doing is drawing the line. All you're doing is drawing this line. What you need instead is that when you're at 0, yes, you need to draw that point, but you need to draw every point here to here. And when you're at 1 here, you need to draw that point, but yes, every point between that. And you have not used both variables. So what we're going to do to remedy this is we are not going to fix our y component with that curve. We are going to let the y component just be v. And we're going to control v here. So v here is going to be between, where do we want v to be bounded between? 0, which is the ground. Where do we stop it though? At this value. -4/3, what? U plus 4. Now let's think about what would happen if we plug in 0. If we plug in 0 for u, right? 0 for u, this is 0, but what's our v? Our v is stuck between 0 and what? That u is 0, right? So 0 and 4. So when u is 0, we move here, u is 0, then our v, which is our up and down, right, is going to be between 0 and 4. So it's every point between 0 and 4. And then as I move and I let u become 1, then it's going to change 0 to whatever that is, which is going to give us every point between there. So we're drawing little line segments instead of drawing just points, and that will give us that whole surface. Okay? That is A. What about B? Let's do B. I only have 10 minutes. So for B, we're on that back side. What's the axes we're dealing with here? XZ, and it is hitting up here at 2 and over here at 3. Like that. Trying to get this region here. So this, if I wrote it as an equation, would be Z equals -2/3 x plus 2. So I'm just using the slope again, is down 2 over 3. It's a function of x, right? Z is a function of x. So what would my R of u, v, be for this one? So what's the easy one? 0 for y. Yes, we're on B, so y is 0. Right? B is back here, so y is 0. And then you're going to control, let's do almost like a type 1 again. Let's control this one between 0 and 3. So let that one be u. Okay? You could let it be v, but then the other one be u. So it's really up to you. 0 to 3. And then v would be between 0 and, I never put what v is. This is going to be our v, right? Our z component is going to be v, and that v is going to be between 0 and this thing with x replaced with u. So -2/3 x, I just said x, u plus 2. Okay? All right, you think you could handle C on your own? Yeah? Let's look at D, because D is more interesting. How about D? So I think for D, it helps if you look at it this way. I'll never be able to get this back to where it was, but I'm about to rotate this. Look at D from the top. If you look at D from the top, what does it really look like? Like, isn't it identical? Like, if you look at it from the top, isn't it identical to A? Yes? Yeah, the only difference between A and D, wow, that went right back to where I wanted it. And then I lost it. Yeah, so A and D, the only difference is the Z component. The X and Y components should be identical. What's happening in the X and Y plane, the XY plane, what's happening there is the same. The only difference is that instead of being stuck on the ground, these points are being plugged up into this tilted plane, right? So what was the vector equation that we had for A? It was what? U, V, and then it was 0. I'm not going to put 0 there. I'm going to leave some room here. And then our U was between 0 to 3, and our V was between that and -4/3 U plus 4, right? Those were the same restrictions. This will draw the plane on the flat sheet, on the XY plane. That's great, but we want to move that plane up and tilt it. So these points here have to lie on that surface, which we need the equation of. So we actually need the equation of this surface. And how will you find the equation of that surface? Take two vectors, cross them, that's your normal, you have a point, you can recover the equation of that plane, can't you? Now I've already done that to save us some time. The equation of that plane, if you do the work, the equation of this plane, I'm going to get B and C out of here and get all this junk out of here. I'm going to get all that out. Okay. The equation of this plane is 4x plus 3y plus z equals 12. So that's if you did all that crossing stuff and put everything together. And what do we do with that? Solve for z. So if I solve this for z, get z is equal to 12 minus 4x minus 3y. Why are we solving for z? Because we're looking for the z component, right? And the z component is going to be the z coordinate of that plane. So now I just take that and plug it in here, right? So I'm going to write 12 minus 4u, because x is actually the u, and then minus 3v. And we leave everything else the same. And this is going to draw the same exact picture, but our z coordinates are now moved up off the ground. Hold on a second. I just realized that that was not the equation of the plane. Well, you don't know that, so no, I kind of cheated because I was going off of my code right here. This is, if you notice right here, this is me telling the computer to plot those four surfaces, and these first three are A, B, and C. So let's see. This one is A. U, V, 0, right? U's between 0 and 3, and V's between 0 and -4/3 U plus 4. That drew me A. And then we had B and C were these two. D was this one, U, V, notice the restrictions, 0 to 3, 0 to -4/3 U plus 4. So that's everything we have here, right? But look at this. When I read this just now, I didn't see the divided by 6, which means this should have been 6z, so please change that to 6z. And then change this to over 6. And then over here, just put the whole thing over 6. That way, if you were to actually go back and check this, like cross product and stuff, you would get the same result. Okay, good? How are we doing on time? We're out of time. All right, so let's just see what we're going to do next time. We're going to try and draw a cylinder. We're going to try and draw the cylinder with the caps on the cylinder, like the both ends, or at least one end is covered. Then we're going to draw this. This is a cylinder. It's been cut at an angle. And then we're going to do this little paraboloid. And then we're going to do this very odd shaped thing. Okay, like a tent, yep. And the idea here is that we're going to then put these surfaces inside vector fields, and we're going to try and compute the net flow through the surface, and that's called flux. But we need to be able to draw the surfaces first. All right, so for the Thanksgiving holiday, all you have is your take-home mini exam. That's due on Wednesday. I accidentally put the 20th on the take-home, but that's on a Thursday.
Are you going to email us this?
I gave it to you in class last time.
Am I the only one that didn't get it?
It's on the web. It's in Canvas too. It should be in Canvas.
Okay.
Go into Canvas, go into Files, go into Fall 2017 mini exams, and it should be there.
Okay.
If it's not, email me and I'll email you a copy. Everyone have a good holiday. You were here, right?